Tree-based models. So this will be quite a trip. What we will do, we will overfit a bunch. We will learn how to overfit like pros. And then we will learn how to deal with overfitting, okay, in different ways. Then we will learn how to build smart models out of really, really dumb models. And then we will learn how to overfit again, okay? So the key word here is not tree-based models or decision trees or whatever, it's overfitting, okay? What you will be learning, so we will build an intuition on different tree-based algorithms. You will learn about rule-based systems, decision trees, bagging, random forests, boosting, and gradient boosting, all in under 15 minutes. This is a first. So, first thing, we will start with decision trees, okay? So, decision trees, there you go. So, in the beginning, there were rules. Why rules? So decision trees are very different, and we will see this from other algorithms in the sense that, think about logistic regression or linear regression. You are learning the betas. You are learning what we call the parameters. With decision trees, you are learning explicit rules. If this, then that. In the beginning, such systems were built with the help of domain experts. Here at FIDS, I would be someone, a fraud analyst, that would be very knowledgeable about different fraud patterns and would, in an interviewing process, tell that to a programmer, and the programmer would hard code all those rules into a computer program, okay? But the thing is, domain experts are rare, and managing rules and creating new rules and deleting rules, it's quite difficult. It's really, really challenging to do. So what if we could learn rules directly from the data without using domain experts, or just using the domain experts to help us build a data set that makes sense? Okay, so decision trees. The first thing, we will look into the structure of a decision tree. I know you can't read, like the lettering is really small, but nonetheless, I will explain you. So you have nodes, okay? Nodes are these rectangles. These rectangles, what you have there, you have the name of a feature, and it's basically a test, okay? So I will do a test on the column outlook, and the possible values for the column outlook are sunny, overcast, and rain. Each one of these possible values, these possible three outcomes of my test, okay, are branches, like Git branches, okay? So I have a node of my tree, and then I have different branches, one for each possible value, okay? And in the end, I have these things called leaps. Leaps is the final decision. And when you transverse a tree from the beginning to the end, you have a rule. So, paraphrasing. So, if outlook is equal to rain and windy is equal to false, then go hiking. If outlook is equal to overcast, then go hiking. If outlook is equal to sunny and humidity is normal, then go hiking. These are rules. So decision trees are nothing but a way to represent rules and a flow chart of conditional decisions, if-else statements, okay? Now, questions. I love to make questions, so hopefully you are still awake. How would you guys go about choosing the first feature and the first split that I will do in my tree? Different ideas. This is brainstorming, and think that, like, you have a hint here, think about overfitting.
Actually explain the target variable.
Why is that? Great question. So we have, just so that everybody hears, we have an answer here. And what's your name? João is telling us that we should probably select the feature that better explains the target variable. Is that it? Okay. So what exactly do you mean by explaining the target variable?
The variance of it.
The variance of it. Okay. So your answer is go.
Maybe I'll put there the most important attributes.
But
that will do the splitting conversion.
Perfect. So the two answers are correct. Okay. But what we are lacking is the intuition. Okay. why do I want to select, basically, and step back again, I want to select a feature that will generate the most possible homogeneous branches. So I want to separate the classes perfectly. So I will select the test that creates branches that are as much as possible all of the same class. Why do we want to do this? Because the shorter the depth of my tree, the less complex my tree is. The less complex, okay, the less overfitting. So what I want to do, I want to build the simplest possible tree that explains all of my observations. And now we know how to select the root node. And you asked me, but we have a bunch of other nodes as well. That's true. But we can go about all those different branches by creating new decision trees, right? So I have a branch here, 2 branches, 3 branches, and I will create, if the leaf is not homogeneous, if it is, then I will just predict if outlook is equal to overcast, then go hiking, because all of the instances in that particular branch are positive. If that's not the case, I can do it all over again. I will create a new decision tree. I will pick up my root node, which will be a test. I will branch again on the possible values of that test, and I will continue until all my leaves contain a single class. Like worst case scenario, I can have only 1 instance per leaf. This is all you need to do about decision trees. Okay? You will have the formulas and so on in the learning notebooks, but this is the intuition. Now, I have a question again. In what case,
So
this one,
in your data set, outlook, humidity, and windy would be the features.
exactly. Tell me.
Windy is the feature.
Yes. All of these tests are features. Okay, so we select features.
And the observations would be P or N.
The observations, the P is a decision. So it means that all the observations in this branch contains observations are of the positive class.
The classes are positive.
Exactly. Yeah, it's started variable. So the question, can you imagine a case where we can't get to a good decision tree, where this algorithm wouldn't work?
If we have the same features for different predictions.
Whoa, you guys are smart. True, exactly that. So imagine that we have 2 examples. They are exactly the same. The features are exactly the same, but the target variable is different. In that case, we will not be able to generate a decision tree. In this case, we call this inadequate features. Okay. So when this happens, we will say that the features are not adequate because they are not enough for us to distinguish different observations with different target variables.
So
Okay.
in that case, the reality isn't good enough for our model.
Our representation, we will get to that in the last learning unit today, but it means that our representation, which is but a simplification of reality, is not good enough.
But what do you do with that variable?
You can do different things. You can either try different models. There are ways for us to make decisions based on non-homogeneous branches. Like you can take the most, the mode, like the target, the class that appears the most, etc. There are ways. But now I really want you just to understand that inadequate features is all about we don't have not having enough information to explain differences in different roles in our data.
Just a simple thing. Numerical things you build, right? You should make everything categorical.
Great question. So this algorithm, I am explaining you, this is from the paper, the original paper. So this is the very first implementation of decision trees. Okay, this is called the ID tree, the algorithm. And you will learn all about this in the learning notebooks. But there are extensions. The first extension is that you can predict, here you can only predict classes, so you can only do classification. This was first extended to support regression as well, and then it was extended to support numerical features as well. Okay, but this particular implementation will only work with categorical features, absolutely. Okay. Guys, let's move on. We don't have a lot of time. Okay, so we already know what could go wrong. And now, I want you guys to, I think this is quite clear, but let's make it explicit. If I have a decision tree with like a very complex decision tree, I have perfect classification in my training set, but my tree is very, very complex, and I only have one observation in each final leaf, okay? This complexity means that I am overfitting like hell. I am not overfitting, I am hallucinating. But really, because imagine I am reacting to all those small corner cases in my data. I am adjusting to those. All those things. So my model will not generalize well. So decision trees are a great idea. And like they are very, very used, but not direct because they are very prone to overfitting. Like very prone to overfitting does not come close to describing how much these guys overfit. There are ways to control it. You can control the depth of your tree. We already know that. Okay. And we can also control how many observations do we want per leaf. We can say, okay, if this split will generate a branch with less than 5 observations, then I'm overfitting. I don't want to go there. Let's keep things as they are, and then I use the mode, for example, to make a prediction for instead of splitting. Okay. So overfitting is a big problem. And sorry.
Can't you control the number of branches also?
The number of branches you control not directly. You control by controlling the depth and by controlling how many observations do you want per leaf. Okay, so I will introduce you now to ensemble models. Ensemble models means that instead of having one model, I will train a bunch of models, independent models or dependent, whatever, different models. Okay, and then I have all these different models. I am training these models with my training data, and then I aggregate predictions. For example, I take the average, or I take the mode. If I have 3 models predicting that the example is positive, and one of them predicting that the example is negative, I will classify the example as positive. Okay, this is the gist. We will learn more about different kinds of ensembling, but this is the gist. So in ensembling, what you do is you try to use models that complement each other in a way, okay? So if these models, if the predictions are highly correlated, ensemble will not help you because they are all predicting the same thing, okay? If they are picking up the same signal from data, this will not help you because they will all be telling the same thing. So ensemble makes sense under certain conditions, and we will see some of those. Ensembles can be homogeneous or not. Homogeneous ensembles mean that all of these models will be implementations of the same algorithm, okay? So I can have a bunch of decision trees here, but they can also be not homogeneous. I can have a decision tree, a logistic regression, and a SVM classifier, okay? And since they work differently, then I can expect them to complement each other in a way. So random forests. Random forests is first thing first. It's ensembling. Okay, so we are talking about ensembling. And how do we do this? Well, we use this thing called bootstrapping. I don't know if some of you are familiar with bootstrapping, but it's quite simple. I have a training data set, and from my training data set, I will generate multiple training data sets by sampling from the original data set with replacement. Does it make sense? So in the standard implementation, all of these training data sets will be the same size as the original data set, and I will be sampling from the original data set until I have enough observations with replacement.
Sorry, what's the replacement?
So I have 2 ways of sampling, right? I have these 2 pens here. I will do random sampling. So I select this one, and then I have a choice. I can either put this one again, and next time I will do the sampling, I might get the black one again, or I can do it without sampling, and this one doesn't exist anymore, and only this one is left. Does it make sense? So I create a bunch of different data sets, and then I will train a decision tree in each one of the data sets. And decision trees, because they hallucinate, they have this thing which is really cool. And this is important. When we are talking about bootstrap aggregating or bagging, critical assumption, instability. Your models need to be unstable. What do I mean by unstable? I mean that if you have slightly different training data, you will get a completely different classifier. And since decision trees and the splits are so particular to the values of the features and they overfit so much, if you have one different training example, you may end up with a very different tree. Okay? So they are very unstable. So since they are unstable and you have slightly different data sets, you will generate different enough trees that then you average predictions or you take the mode, and this is a way for you to control overfitting. Okay? You have different data sets, you train a bunch of models, and then you average them. And it's a way for you to control overfitting. Bagging works really, really, really well in managing overfitting. It's a quite simple concept, but quite a powerful one. Tell me.
So the intuition is I overfit on small parts of the data set. So when I average it out, I'm not overfitting.
Yeah, that's the intuition. Although you should try to keep overfitting to a reasonable amount. Like overfitting like hell, even here in these specific models, is not ideal. You want them to pick true patterns in your data. Okay? What you want them to do is to pick up different patterns so that when you average them, you will get more accurate predictions and you will get less overfitting.
Does it mean that the more bytes you have, the more
in theory. In theory.
How about in practice?
In practice, it really depends on how much signal do you have in your data. If you can have a very high complexity, but if you don't have enough data to train that complexity, or if you don't have that much information to benefit from that complexity, you are just over-complexifying.
So we probably reach like a point where it starts to converge, where you just go ahead and add more estimators, and then just
nothing changes
except for your runtime.
Absolutely.
What do you mean by more signal in your data?
So information. So some of the information in your data are true patterns that you want to learn and that you want to use to make predictions because they are generalizable. And that's the signal. That's what I mean by signal. Great question.
Thank you.
So guys, I will have to move on. Then hopefully this will be more clear in the learning notebooks. But I want to tell you more about random forests. They are powerful. And they are powerful not only because of bootstrapping. Okay? They are powerful because they take more measures to prevent overfitting. We can think about bootstrapping, taking a step back as, and I'm sorry for this, as row sampling. I am sampling rows, correct? I have my original training and I am sampling rows from that. Well, I am including some randomness in my model build, okay? And what random forests will do, they will, each time you will do a split, and this is pretty cool. So imagine that I will do this split over here. Only a random subset of the features will be available at each split. So we will be at each split effectively sampling rows as well. Columns. Thank you. So we will be sampling columns. Not all the columns will be available for me to make this split. Only a random selection of them. Can be like 3 of the, imagine that we have 20 columns, only 3 random columns will be available for me. This is a kind of regularization, if you will. So basically I am controlling the overfitting by introducing more randomness and forcing my trees to learn different things. I am really forcing them to learn different things by introducing randomness. So I am controlling overfitting by using row sampling and combining it with column sampling. So this is really good. So I am effectively managing overfitting, but I am losing some explainability, some interpretability, because I am including this intricate process, and at the same time I am including randomness. So explainability is hurt, but I do a great job at managing overfitting by using random forests, and this is why random forests are so powerful. Okay? Deep breath. Are we making sense so far? Okay, let's go. Gradient boosting. Gradient boosting, let's go at this really, really slow. Imagine like when we were building the random forest, we are building several models in parallel. What do I mean by parallel? These training sets are independent. Like I generate one training set for each model, and the models, the predictions of the models they are not dependent on each other. So each model generates its own independent prediction. They have their own training data. We train them. They will tell us positive class, negative class. And then we combine them to make sense of it. But they are completely independent. So I am training models in parallel. What I do with gradient boosting is I am training models sequentially, not in parallel. What the hell? Right. I was just resting random forests and then you changed everything. So I have my training data. Okay. My original training data is my original data set. I will, important thing, you guys need to hold me accountable for this kind of thing. All those models there are decision trees, okay, in the random forest. The individual models are decision trees, all of them, okay? So, back to gradient boosting. I have my original training set, I will train a tree. And I will train a tree stupid like hell, really, really stupid, like shallow, with like depth equal to 1. I do a single split. It will be really, really dumb, okay? To make sure that I am not overfitting. And then what do? I will generate a new training set. But my new training set will know the error of my past predictions. What am I telling you guys? So I have the original data. I train a model to make predictions on that original data. I know what are the cases that I am getting right and what are the cases that I am not getting right. In the case of regression, I actually know how much, and classification as well, how much am I mistaken? Okay, I know that because I have the true label and I have my prediction. I compare the two and I have my error. And my new training set will include all of the same features. Well, we will see about that, but will include all the same features in my original data set, but I will have a different target variable. And the target variable, I will try to predict the error of this model. Let it sink in. Okay?
Can you say it again?
I promise. So imagine that I make the first prediction, I have a prediction, I know how wrong I am, so I know, should I be, imagine in the case of regression, should my prediction be higher or should my prediction be lower? By how much? And I will train the model to learn this.
It's correction on the model.
Exactly. I am learning models to correct the previous model. And I will do it again and again and again and again and again until convergence, until I am not improving anymore. Okay? This is the basic intuition. Now, this is oversimplified because gradient boosting is way more powerful than this. We are not just fitting on the error. We can do better than that because we know already, all of us, how to do better than this. Because imagine, it's cool for me to know how wrong I am, but it's not, you know that we are not optimizing for that. We are optimizing for a loss function. And we want to use whatever loss function we want to. And I can use gradient boosting to optimize any loss function for as long as I can differentiate it. How can I do this? Instead of using the simple error, I will use my derivative in the point for each line. Think this through with me. The derivative is a slope, right? Is a slope in my error function. And I can know the derivative in the particular point. Why? Because I know the value of my prediction and because I know the true value. If I look at the slope tells me not only if I am right or wrong, it tells me where do I need to go to reach the minimum. And what I will do, it's a fun thing. This is really fun because what I will do is, this is my hypothesis, okay? And in t+1, so I will be updating my original hypothesis, and this will be equal to my ht, okay, my previous prediction plus a learning rate times my correction. And you know where I am going, right? And I will repeat this, and repeat this, and repeat this. You might call it gradient descent. I am.
Appreciate the effort.
But you are basically always correct. Now, back to reality again. Why is this even useful? I know that random forests are really good at managing overfitting. Boosting is really good at managing bias. Because I can train as many models as I can, or as I want to correct on previous predictions. So in theory, I can get to a point where all my predictions are correct. Because I can keep on correcting the predictions that are not correct, right? So this is a way of building a really, really robust two-bias estimator out of really, really dumb estimators. And you tell me, okay, I can use random forests to manage variance and overfitting. I can use gradient boosting to manage bias. But the main problem with decision trees is overfitting. So we are back to overfitting in the way we are. So we need to be really careful. But gradient boosting gives us tools to manage this overfitting. So I can combine all of these with bagging, for example. So instead of these training sets, I can use bagging. And instead of using all the observations, I can use random observations. A bunch of them. I can sample observations. And in my trees, the trees that I am building, I can also use random column sampling. And at each split, I will only use random features. And that way, I am also trying to manage overfit and variance. So gradient boosting is really, really, really powerful. And in my experience, it's like the results are usually great, okay? And this is how it works. You will have all the formulas or all the math, etc. You will have it in the learning notebook. So you can go really deep if you want to, at your time, at home, etc. You don't have to understand everything like today. I am still learning myself every single day. So it's perfectly normal. So I want to recap because we don't have a lot of time. So recapping, decision trees are a way to learn sets of rules from training data without using the domain experts. Unfortunately, they are really prone to overfitting. They are really, really prone to overfitting. They always overfit. Okay? Random forests are a great way to control overfitting by using bagging, which is bootstrap aggregating, sampling rows, and combining that with column sampling, sampling columns, okay? And they are good at managing overfitting. Gradient boosting is a great way for us to minimize a loss function, whatever loss function we want to minimize, and to reduce the bias of the combined estimator by using really, really, really dumb estimators, okay? Both random forest and gradient boosting improve the performance of decision trees at the expense of interpretability due to the randomness of the process and due to using intricate procedures that are not immediately easy to comprehend and to explain to a business guy or whatever guy. It's tricky, it's not easy. So guys, you are now experts in random forest, gradient boosting, and decision tree. Hopefully you enjoyed the lesson. Let's get